Hi everyone. Today we're going to discuss about one of the hands-on exercises that's uh, required in distributed databases, data partitioning. Given a data base, it can be divided into a smaller, not necessarily smaller, but compared to the given original database size, it could be smaller, but still that is too big, and it can be each smaller. The partition uh, can store it in a different databases. Okay, so what is partitioning? Data partitioning. That is dividing a database into smaller and more meaningful pieces called shards, which can be distributed across multiple servers. So uh, data can be uh, partitioned uh, in based on specific range of values. For example, user ID 1 to 1000 on one shard, 1001 to 2000 on another shard. If you are thinking of, for example, the president, the elections, then when you go to the election voting place, and in order to get the ballots, then there could be multiple different shards available. So then you approach it to one of the desk, then you can pick up your ballot. That type of things is range partitioning. Another case is still there's a similar partitioning, but we call that hash partitioning. Databases can be partitioned for given fixed number of shards. So we can distribute database the uniformly based upon the hash functions. That is the modular function like this in, for example, Pythons. Yeah, another way that you can divide the data based on a list of predefined values. We can call that list partitioning. So if we are considering some of the electronic commerce, then orders from specific regions goes to specific shards. That is reasonable, right? You don't need to keep all the products in one location. If you consider the entire the country, let's say you store that in Florida, then lots of cost, the logistics cost involved if you send products from Florida to Washington states. So you need to make a multiple distribution center like Amazon business. So there is a list of partitionings. Composite partitioning, there's a combinations of above. So outcome of a partitioning, we end up having the data can be horizontally partitioned or vertically partitioned. Example for that is, let's say if we have employee tables, something about the employees, then we can partition that horizontally. We call that DBH, DBJ, DBK, different database. It could be in one server. It could be in different server. Okay, DBH may be in Google Cloud Server. DBJ may be Amazon Cloud Server. DBK may be driver site server. So it could be Raspberry Pi database. All right. So given the same schema the data about the same schema can be distributed into multiple databases. So let's say DBH has a number of tuples like this. DBJ has a number of tuples. DBK number of tuples. The data type that we looked at here is a dictionary data type. So in this dictionary, you could use a different way, but this is one of many possible implementation approach. So the key in this dictionary is the database. DBH, there is one database. DBJ, another database. DBK, another ones. And then the tuples that you can see here, they are all different, right? It could be divided by many different ways. Let's say if it is a salary, then salary, you can divide that depending upon the salary, or you can divide the employees depending upon the department. All right, many different ways. So there could be some partition rule available. In this case, we don't use any partition rules, but that is possible, right? As we looked at here, some range partitioning or list partitioning. Hash is more mathematical way of partitioning. Therefore, it may not be a real rule, but it could be a rule, yeah, if you say, okay. So this is a horizontal partitioning. On the other hand, we can think of vertical partitionings. So example of partitions, let's say if we have a CID, name, address, PID. CID is a customer ID, PID is a product ID. So product name and product price, the customer name and customer address, and then quant, how many the products is ordered and expected to arrival, some delivery time, maybe also another attribute here. For simplicity, we put here text, but you can put there as date if you like. Okay. And also there are 4 locations of databases. We call that DB-all, DBS, DBT, DBV. If you see here, then there's a vertically. So part of these attributes stay here, another subset of the attributes here, another subset here, another subset there. For the example, see here, DB-all has, for example, customer ID, customer name, and address. DBS has product ID, product name, product price, and DBT, this is more like order, the placed. So customer ID and product ID. Customer ID ordered some products in this amount, this quantity, and therefore there is a foreign key. Just the CID comes from here for customers, and PID comes from products there. Okay, and then finally we can think of DBV for deliveries. So PID, delivery has the information, product ID and quant and address, and some expected arrival time. Okay. So real examples, as you can see here, this is for customer information. This is the products information. By the way, this database, this data examples is very similar to the ones that we looked at already in one of the previous homework assignments. This is an order, and this is deliveries. So each truck has some of the database that can run on Raspberry Pi. Okay. Maybe customer database is maybe in cloud server, products database maybe in another cloud server, okay, and order information in somewhere in distribution center. That could be another cloud server, or it could be a laptop computers. So distributed query processing requires some of those techniques. Query decomposition. Given a query, the answer to that query cannot be given from one single database, but from multiple databases. Then there's a multiple different databases located in different locations, different platforms. Therefore, you need to, if you send out the same query, if each of those distributed databases is not defined over the same relational schema, if they do not hold the same kind of tables, then such query cannot be handled. So you need to send a subset of the query to a small database, and those query, that small decomposed query should be handled completely well in that given small database. So each of those decomposed query needs to be handled in one single database. In that way, you need to decompose the given query. This is the data location. Therefore, you need to send it to a query to a specific location. And in that location, of course, optimization is needed. We need to reduce the cost. For example, if decomposed queries can be handled because it is distributed to multiple databases, and if it can be handled same time, then parallel execution will be another good way of handling distributed data, the query processing. And then from each database, we can collect the answer. The answer from each database is not the complete answer. So you need to collect them and aggregate them. So result to aggregation is needed. That technique can recompose the multiple the response, each of which comes from a small databases. Of course, each of which is not complete yet. Each of them is all partial. Therefore, you need to aggregate them. And then finally, of course, you need to consider the fault tolerance. So distributed system must be resilient to node failure, redundancy, data replication, checkpointing are often used to ensure that queries can still be processed even if a node becomes unavailable. A node means that is one network node, therefore one cloud server that will be a node. Once we partition and distribute data into each participated databases, then query can be decomposed. Decomposition of a query can, depending upon the partitionings, horizontally partition the database or vertically partition the database. Remember that if it is horizontally, then schema remains the same among those databases. if it is vertical partitioning, then schema should be different. One subset of a schema available here, another subset of a schema here, another subset of a schema there. Therefore, your query decomposition is more complicated. Let's say if a query covers a limited databases relevant to partitioning rule, if there is a partition rules, then we need to use that partition rules. Queue can be decomposed accordingly. Sometimes we can use a partition rules. If query needs to go to each of those partitioned databases, then we simply distribute. Queue can be posted to all databases. Queue means same queue, right? Given queue. Let's say if database data are vertically partitioned, and that partitioning was made based upon partition rules, then if given query requires a limited database only, queue can be posted to those databases. Given query cannot be distributed to all the partitioned databases if it's not needed, right? Then we need to know given query, how many tables that given query is to be processed. Otherwise, the query can be posted to all databases. In our hands-on exercises, each of those examples are also considered. Once query is decomposed and the result returned from each partitioned database, then we need to aggregate the result. If it is horizontally partitioned database, then we simply union all, because they are the same schema. If a vertically partitioned database, here's a real complicated, right? Depending upon the query expression, sometimes it is really, really complicated. The heavy duty query processing is needed. So example for the horizontal partitioned database. Let's say if database about employee is partitioned horizontally, then each partitioned database contains the data about the same schema. So each partitioned database has employee, table, and this kind of attributes is available. Therefore, we can post to each database, and then we can collect later. Another way is that if we say salary is greater than or equal to 80,000, then depending upon the partition rule, if data is partitioned based upon salary, then we don't need to send out query to all the database. Only we can send to a specific database, right? Because these guys can be only available as a small subset of the entire database, because it is partitioned based upon salary rules. Sometimes it could be the rule can be something about the department. Then we can use the department information there. This is for the case of a horizontal database for distributed query processing. Now we can think of a vertical partitioning case. We have a customer database, products, order. By the way, I put here a double R. MySQL, if we say order, then you will have an error. because ORDER literally is a reserved word. So you definitely, order cannot be used uh, in your MySQL application databases. Therefore, I put here one more R. So 3 databases available, and they can 3 tables, 3 databases are joined. Okay, and then we have aggregate function, group by name. So basically, this query wants to see who placed the orders for how much. Okay, so we can see the name and how much of data that that person ordered. So based upon those 3 databases, we need to be distributed the database precisely. Some of the data that is available from customer database, another attribute may be available in products. For example, price is available from the products, and order quant that is available from the order database, and name that is available in the customer. Therefore, those 3 tables needs to be considered, but query cannot be posed to. It's not the case that the same query that can be posed to each of those partitioned databases. So we have to rewrite. We have to decompose this type of queries. Okay, decomposition itself is not simple because query expression is not simple. See here, this is one query expression. Another query expression, we may have another the condition here, right? Without, this condition, without this condition, 2 queries are the same. Here in this case, we need to see only. I want to see only the query, only the items. Expensive item is ordered. Then I don't want to see the list of the customer names together with the amount of the order. If we have this and that, they are similar, but the real processing is not simple. Similar, but processing is not simple. So complexity of distributed query processing, we have to first consider lexicon analysis. So we have to, the query expression requires some query grammar, right? So the expression needs to be analyzed based upon the query grammar. Each DBMS has different grammar. Most of the DBMS uses the standardized grammar, but companies that enhance their query expression grammar differently. Therefore, lexicon analysis needs to be involved in order to decompose and also in order to aggregate the result of those. So decomposition is not simple. First, we need to understand the lexicon, not the human, but our code, our Pythons needs to be dealing with such complexities. Query optimizations, network latency and data transmission, query, again, aggregations. Part of this that we can exercise in Python, but we cannot do all of these, right? This is a real commercial, the products, but we can try to see small particle of the distributed query processing. More complexity comes, for example, if there is a multiple replica, N data replica in M databases, or there may be X role-based access control in Y databases. All different situations needs to be considered in addition to the query distributed query processing optimization itself. So lots of things needs to be considered for distributed databases. In a wide range, if we consider, then let's say MySQL database in the different platform, right? In cloud server, and also file database needs to be considered also, not only SQL, not only relational database, but file systems needs to be involved. How can we aggregate? How can we decompose? For example, if this file database is in mobile server using API, or definitely we can think of our system running on a laptop, but we can include a graphical user interface as well, right? In our laptop, graphically, we click, then it goes to, for example, the cloud server. It goes to the other components, maybe shipped to RPI, Raspberry Pi server or mobile servers, all different scenarios available. Pictorially, for example, this is a laptop and your cloud servers and Raspberry Pis. From your graphical user interface on laptop, by clicking some of the buttons, then it goes to some here and some there, right? Cloud server is not only one, but more than one. Then what should we do, right? All those things needs to be done. So this is the concept, and I made a small exercise, small implementation. I want to include credentials, import credential. If you see my credential, this is a credential, okay? So you can write your host, user, password, database, port of your credentials, and you need to include that. So import that once, and user, and then when you connect to your MySQL, then from this my credential files, MySQL server is assigned to user. Similarly, MySQL password to assigned to password, and host and port. Having this method connect, so that we have an object of connector, which is called CNX. By the way, before we do, in order to get this my credential into database, I mean the Python, then you can simply copy this, import OS. The way here is that wherever this Python code available, and if there is my credential, this credential files exist in the same directory, then they can be understood each other by having this. So import mysql.connector, and this is second import. This is for error handling. So having from these statements, you will now on object of a connection. So you have a connections. Once you connect your database, then you have a cursor. Okay, that cursor, this cursor can invoke a method called execute. So within this execute method, you can do your MySQL the language, for example, show databases, or or somewhere here, cursor execute drop databases, and create database, and then create tables, cursor dot execute. Then some of the table creation statements can be executed. Populated data, then also some insertion expression language can be executed. Here cursor dot executes. Okay. And finally, query can be processed. So this is the DB. Remember that this is a horizontal case. Each query needs to be decomposed separately, and each decomposed data, the query expression needs to be posted to different database. In this specific database, we need to execute a specific queries. Okay, so you first need to use database. You need to change the database, and then this is a query expression. So you need to execute the query, and the result can be this cursor dot result is in this cursor. So the result can be fetched by fetch all, and then you can display some of those, and also you can return the result. So what it does is that, let's say if we have 3 databases, so DBH, DBJ, DBK, that's what we considered in the example of a database. And then query, the schema, remember that if it is horizontal, then one schema, the same schema remains. Same schema is used for all the databases. So ID and name, department, salaries, okay, and then the populations data. So for DBH, we have these tuples, 3 tuples. For DBJ, we have another 3 tuples. For DBK, another 3 tuples. Okay, that exists. So first we need to populate. We need to first create tables, right? So we send this tables. When I send, I need to send this schema create table expression and then I need to do, for example, split 5, then 1, 0, 1, 2, 3, 4, 5. So when I send cursor and three arguments, right? 3 arguments three arguments are used to invoke the create table function. So second argument here is the table name, and third argument is the entire table expression. So if you go create table, then this is table name. Only reason that I need to see this table name is because I want to display the description of the table. Table schema needs to be described here. And then query processing, I can say, hey, you need to do this, and then database, and we send this query queue process. The same, because this is a horizontal the partitioned database, then we simply post the same query, for example, right? So same query, same Q1 can be assigned. Okay, so, and also we can do, one time we can use this simple query, and then also we can do a little bit of complicated queries. We have a where clause also. This can be executed in, I want to execute it in separate tables. So this is the code, MySQL, I mean the SQL embedded Python code. And I want to see. So I have dist horizontal dbs.py. So Python dist horizontal dbs files. So up to this points, see here, first database available. So in my database, I have 505 DB, CY 525, and so many difference. This is my exercise: DBA, DBC, DBF, DBH, DBJ, DBK, RS, TB. Remember that in our examples, I already had that. So if it is already available, then I first drop it and then create it. So schema of employees is this. This is the schema information. And then insert. I can insert to this database DBH. This is one of database. I insert I believe that is a 3 tuples, and then once population is complete, then this is another check. Remember here, population is done. Then we can say select the stuff from where I want to display the data populated in employee table at DBH, this database. So the result of that is here 3, only one, I think, this. And also another insert. So first I insert Alice, and then I insert Bob. At this point, the database contains the data 2 tuples, Alice and Bob. And further to the same database, I insert Charlie's. Therefore, this DBH finally contains Alice, Bob, and Charlie all. Once I have done that, this database DBH, then now we consider DBJ, second database. First I need to drop, and then create the table, same schema, and I insert. And therefore this DBJ has also 3 tuples of data. And finally DBK, third database. So DBK has also 3 tables. Now I can do the query processing. So if I select this, I want to select all of those. Simply copy and paste here and enter. Then it gives me this is what I did, right? So from DBH, I collected 3 tuples. From DBJ, another result, and from DBK, another result. So aggregates them is only I union all of those. Therefore, the result is in this list has 9 tuples. Of course, you can, for example, display that in very nice table forms. But in this simple example, we simply see the Python data, a specific Python data type. We can do this a little bit more with, for example, I want to with this and then where close. Where salary is greater than or equal to 8,000, 80,000. Then here the final result is only this, right? Only 80,000 or above. Remember that the previous result all the way up. See, previous result, final result is this many, right? All of those, but in this case, only those. So now move to the vertical partitionings. Most of them are similar. Query processing also similar. Only we have 4 databases, and then table schemas. Also, I have a different database has different schema. Here, create tables up to here. That is about customer. Second database, DBS, has the product database, and then DBT has the order. Here, order, double R. Remember that I explained that, right? And CID and PID has foreign keys. Look at here. Foreign key references. Then customer is not in this database. That is in different database, which is DBR. Then you need to say here DBR dot customer. That's CID, because CID is referenced by this CID in this table. But that is a foreign key, right? This is a foreign key, and its own original primary key is in the customer, is in this database, customer all database, and customer table. So we need to specify that in this way. Database dot table, open and close parentheses, and attribute name. Same thing. Product ID, that's not defined here in order, but defined in another database, DBS, and where there is a table, products, which contains PID as a primary key, PID. So we need to say dbs.products, open parenthesis, PID. This is something different from the other. Okay, so a little bit of decomposition issues, and also this query processing is a little bit different. But anyway, so if I run this, okay, Python distribute vertical, vertical, let's see, ls minus nt. Okay, Python okay. So they are partitioned. If you see here, let's see, for example, DBB, this is a delivery. Then in this deliveries, DBB has, say, data populated in the delivery at DBB is, this is 111 is the CID. I do not know what customer ID is. 111, we can see above. 1111, this is customer, and product number 1. And Broadway, this is the address to deliver. And then estimate to arrive, this is today. This is also today. The other one is tomorrow, and the other one is undecided. That type of things. This is data populated, right? Data created and populated. Another database here, order, DBT. So data populated in the ordered ones here. Oh, this is a customer. Here, 111 is not customer. This is a product's name. And I think one is quantity. How many ordered? This is 111 is customer ID. 111 is product ID. And this is a quantity to order. And above, DBS, then this is a product table is stored in DBS database. Similarly, here this is products database. This may be customer data. Well, customer table that's stored in DBR database. So 111 is John, Broadway, 112, Sam, Main Street, things like that. To this vertically partitioned database, this is an example of the query. So that if I use the same query and enter, then result here is okay. Here, the issue here. Remember that aggregation and decomposition, that is very, very complicated in the vertical partitioned databases. I didn't implement it. The implementation requires, I think, hundreds and hundreds developers and millions hours of work, right? So I didn't do that, but I simply collect the data, and then we need to further process. So what I did here is I simply get the data and append it to the result. If I have a little more specific query expression, like products.price is greater than $50, little bit more expensive products is ordered, and if I want to see it, then I can use that here. The products.price is greater than or equal to 50, then I might have a smaller set of data sets, but I didn't aggregate this yet, right? So from the possible data sets, then I need to process. Okay, I need to join because each of this comes from different database. For example, from here, look at this is entire is a list. List contains a sub list. For example, here this is a sub list. As this list comes from customer table, another list comes from products table from here there, and another list comes from the order, and therefore we need to process this. For example, 111, then it needs to be joined with the products, because we have a 111 here, 1111, there's a products ID. So join operations needs to be implemented and optimized. That's a quite big project, okay? But in this simple example I showed to you, simply data can be fetched from each partitioned database, and we need to do a lot more additional work as we looked at, for example, What was this? No, as we looked at. Right here. But anyway, I'll skip here. I already explained that. All right. This is a hands-on lab for distributed database, partitioning and query processing. Query processing is not completely done. Of course, that requires a lot of work. Okay. All right. I'll stop here. Thank you.